Hello, welcome to today's video. We'll be looking at an algorithm, the missing number algorithm, and it's a very simple algorithm, easy as we can see here, just an easy algorithm, and just explain it briefly and go from there. We'll try and look at it from few angles, but we'll just use one of those approaches to solve it actually here. So we are told that given an array norms containing n distinct numbers in the range of 0 to n, that will return the only number in the range that is missing from the array. So for example, we're given nums to be 301 and the answer is 2 because 0, this is going to be the length of this array is 3. So starting from 0 to 3, 0 is found here, 1 is here, 2 is what is missing. 2 is missing. The second example, 0, 1, the length is 2. So it means we are going from 0 to 2. Definitely 2 is missing here. Here the length is 9. So we are going from 0 to 9. And 8 is what is missing here. And we are told that all numbers are unique. I just also told that we could solve this in O of 1 space and O of n time complexity. So let's see how we can go about solving this. Let's look at the different angles we can come about solve this algorithm. So we have where we have a norm, that is our array 3, 0, 1, and one approach is that we start from 0. We know that since the length of this is 3, so we know we're going from 0 all the way 3, and we say at 0 check this array, does it exist? uh, it exists, so it ticks that, means we're fine. Goes to 1, does 1 exist? It says yes, 1 exists. It goes to 2, it says does 2 exist, and it doesn't find it, so it knows that automatically the number we're missing is 2, and then it returns 2 as the answer. So basically that's the first approach. But this approach, if we are going through the array like this, it will be an O of n square, because we'll be going through an array, iterating through an array is O of n, and we're also going through the list from 0. We are going from 0 to the highest number, which is the length of the array, which is another O of n. So, and they'll be within each other, so that gives us an O of n square. That's how we have an O of n square. But that is not optimal enough for us, so we can optimize this by probably creating a dictionary first of all. So for example, we can iterate through this and form a dictionary that will look something like this. So when we go through everything, we have 0 is true, so this is just a dictionary. We have 1 also true, we have 2 no, so 3 is also true. That is going to, so when we have gone through the dictionary, this is what we will have. So we can now go through each of the items and go through. So we go through again and we are asking if each of them are found there. So for example, ask is 3 in this I mean we start from 0, so from 0 to starting from 0 to 1, 2, 3, all the way to 3. So we start from 0. Say is 0 in this dictionary? Definitely yes. So that's fine. Is 1 in this dictionary? Yes. Is 2 in this dictionary? No. So we know that 2 is the answer. Now, this is more optimal. So for the time, it means we just need to go through it. O of n. It's an O of n. So that is just still going to give us O of n algorithm. So that is the time complex. But for the space, now it means we also need an O of n space, because if the length of the array was 7, it means we will need a dictionary that will contain 7 items. So that is the space complexity for this. But we have been told that there is actually an approach where we could have a space of just 1, a constant space. So let's look at it again. So I come here again, let me just have it here, 3, 0, and 1. So looking at this thing, I know that since it's since I know that it's supposed to go from 0 all the way to 3, I can say that 0, 1, 2, 3, and I know that if I sum them up, so 0 plus 1 plus 2 plus 3, I am expecting this to be 6. So, but in our own situation, we have 3, 0, and 1. If I sum this up, what I have is 3 plus 0 plus 1 is 4. Now, the difference between what should be the sum if everything exists and the sum currently, which is deficient of 2, for example. So 6 minus 4 will give us 2, and that gives us the number that is missing. So this is a very, very simple approach, and it's an O of n for the time, and for the space is constant space because we are not assigning any variable. We are just going to return. We are not assigning a variable that increases with the input size. So it's going to be a constant input size. I mean, constant space, because it's just what we will be returning that we need to remember. So basically, this is another approach. There is another approach, but I will leave that to us. So it's an X NOR approach. We have the truth table for XOR, something like when we have 1, 1, it gives us 0. When we have So basically for XOR, it is when the values are different, we have a 1. But when the values are the same, we have a 0. So we can use that to our advantage because we know. So for example, let's say we have 3, 0, and 1, and we'll compare from 0 all the way to 2. Sorry, 0 all the way to 3. So 0, 1, 2, 3. So ultimately, I know 0 we go with 0, 1 we go with 1, 3 we go with 3, and all that will be left is 2. So that is what the XNOR approach actually tries to utilize. So you could research into that. It's very straightforward too. Lastly, there's another approach I would like us to look at. Let me just create some space here for us to. So another approach we could use, which I find interesting also, is that given that we have 3, 0, and 1 as our array, we could start from the first, and we know, okay, this is 3, so it's beyond our array. So we know the array size, so maybe I break this into an array size. So, okay, so it's just 3. Sorry. So we have index 0, index 1, index 2. So this is 3, 0, 1. So we start from the first item, 3. 3 exists, but it's beyond the length of this array, so we can omit that for now. We go to 0. So 0, so what will happen now is that 0 we swap with its index. So whatever this value here is 0, we will swap. So we'll go to index 0 and put 0 there. So what we will have next after this point is something like this. So we will have 0 here and 3 will be here. So this will be it. So so we have swapped, and then we swapped with 3, so we are now at this point now. So 3 is also still more than what we want. So we go to 3 is more than the array size. So we leave that. We go to 1. So 1, we go to 1. This is index 0, index 1, index 2. So since this is 1, we go to index 1 and swap with whatever is in index 1. So this will come here, and then this will go here. So after this, what we have is something like this. So we have 0, 1 will have swapped here, and 3 will have swapped here. So we are at this point here. This is where we swap to. Now at this point also, we say 3 is more than the index, and we go to the next. We are out of bounds, so we know that that's the end. And so we can now go through it. What will have happened is that it will have sorted the array, so we can come and check, and we can check this is 0, is 0 existing, yes, is 1 existing, yes, plus 2. So we expect at index 2 what should be there is 2, but since 2 is not in index 2, we know that that is the missing item, and we can return 2. So basically that's, so maybe I use a bigger sample space so that we can see it clearer if the sample space is bigger. So let's go with something like 4 3 1 2. Okay, so let's say 0 is what is missing, and 5. So I am missing 0 1 2 3 4 5. Yes, so what is going to be missing here is 0. So we start from here. At this point, what we have is, so we have 4 3 1 2 5 at the beginning. So we start with 4, and we know this is index 0, index 1, index 2, index 3, and index 4. So we start from here, 4. So we'll swap what is in here with what is in index 4. So after this, what we'll have is something like this. 5 will have come here. We'll have 3 1 and 2 here, and we have 4 here. So at this point we have swapped to this place. So 5, but 5 is more than what we can, the index of the array. So we go to 3. So this is 0, index 1 2 3 4. So we come to this index 1. What we have here is 3. So we go to index 3 and swap with whatever is index 3. So we swap this. So what we will now have is, we have this. So we have 5. We have 3 will have swapped with 2. So this will be 2 1 3 4. So I am still at this point, but so I am here now. I am still at this point now. So I ask myself, is this is index 0 1 2 3 4. So we check again. This is index 2, but this is, I mean, this is number 2, but this is index 1, so it means it's not in its correct index. So we swap again, index 2 with index with this. So at this point, after we swap, we have something close to this. We have 5 here, we have 2 here. Okay, sorry, I will have swapped, right? So I have 1 and 2 will have swapped. Then we have 3 here and 4. So we are currently still here. So this is 1. So this is 0 1 2 3 4. So this is 1. 1 exists in 1. Fine. So we go to the next one. 2 exists in 2. So we go to the next. 3 exists in 3. So we go to the next. 4 exists in 4. So we go to next, and we're out of bounds. So if we go and start counting from 0 all the way to 5, when we start with 0, we check is, so we iterating from 0. Is 0 in index 0? The answer is no. So we know definitely the missing number is 0. So this is another approach. It's also going to give us, or because we'll just be going through from here to here, that is just O of n, and we don't need to create any new space because we're using the same array. That is still going to be O of 1. We're not, our input size, we are not creating a variable that changes with our, since we are using the same array that we are given. So this is another approach. So of all of these approaches, you could use any one and we will get a correct response. But I will just go for simplicity's sake and use the sum approach, since that is very easy to understand. So basically we just need to get the sum, and I could use, so we could use the for loop, just basically nouns.length And so since we want to, so we'll call this the original sum. So what we expected it to be, so that would be original sum was equals to nums I, and then we can get the actual sum, and that will be just based on what is in, so for each num in nums, and basically we'll just be summing up actual sum, and then we know our answer will be 1 with the original sum minus the actual sum, and this should give us a correct, let's see. Okay, so it's the index out of bound. Oh, sorry. So I don't need to, so all I just need to do is sum the I. So I want to sum 0, 1, 2, 3 all the way to the length. So I'm not supposed to index that. So let's try again and see. Okay, so it passes this case. Let's submit and see if the code is optimal and correct for our situation. And yes, it is. So that is how we can solve this missing number algorithm. There was different approaches. I hope we enjoyed this video. See you next in the video.